So I think there was a question regarding display resolution. So I think it's all given on Wikipedia. If you go here or you type in the Google, like we just type mobile display resolution, so you will get here, and it's all given here. So 1024,768. So aspect ratio is one thing. It's basically width over length that will give you the aspect ratio. So, and it depends on the shape of the display also, if it's square or rectangular, or width is more than height or height is more than width. So that gives you aspect ratio. So you can get a different pixel size in x and y direction. And then if you move here, so this is your um, in row and column display size. So you have a different number of pixels on x and y. And then so resolution is mostly measured in terms of pixel density, which is PPI. So if we, let's say we have a 1280 by 720, which is for 4.3-inch display. So obviously the number of pixel per inches will be more compared to 4.7 inches if you have a same number of pixels, total number of pixels. So when your display gets bigger, in order to get a better picture quality, you have to increase the number of pixel. And then eventually you may have to move to let's say from 1280 by 720, let's say you are moving to 1334 by 750. So now your pixel density is increased. So and then as you move on 6, so let's say 6 inches display, obviously it may require more. So now pixel density is more, and now you are moving to 1920 by 1080. So more like a HD or full HD display you would have seen. Then ultimately you move to 4K 4K display. So I think 4K is somewhere here. Yeah. Okay, so this is your 4K UHD Ultra E. So that's how, as a resolution increases, or you can say pixel density keeps on increasing, you just move from HD, then you have a QHD, then you have a UHD, Ultra HD. So it all depends on the size of the display and how many pixels you have, and you just multiply the pixels and divide by size, and you will get pixel density. So I mean, if you are using, let's say, this particular display, so let's say 1080p. So if you are using this in a 6-inch phone versus a tablet, which let's say 8 inches, then obviously 8-inch on 8-inch, the picture quality won't be as good as which you are looking at 6-inch. So because it's a smaller display. When you move on television, your pixel size will increase automatically because you have a same number of pixels in x and y direction. So, and your power management requirements will change according to the size of display. So now it's quite possible that a bigger display, if you want to maintain the same resolution as a smaller display, it may be divided into multiple sub displays. Okay, so then your power management requirement will also change. So let's say you have let's say 2 6-inches display combined together, you divide in two halves, and you can put like a two separate drivers for each in parallel, and then your power management each will require its own regulator, each segment. And for a backlight also, like let's say your cell phone requires 4 to 8 LEDs, but if you are looking at a display, it may require like maybe 10 times more LEDs for the backlight. So what happens, each bigger display will be divided into subsegments, and each will have its own backlight, each segment, and they will have their own driver. So if you look at a total number of power regulators, maybe more, or the current capability of the regulator will increase if you are using single regulator. So the power, obviously power requirement will change based on the size of the display and resolution both. So let's see how we generate these supplies, plus minus 5.5 volt, and then the backlight, which is higher voltage. So for plus 5 volt, you can simply use a boost converter, and boost converter we already covered in one of the lectures how it works. So it's a simple inductive boost regulator, and we know the output voltage will be 1 over 1 minus d times into V bat, where V bat is the battery voltage which is changing from 2.7 to 4.6 volt. So based on the voltage, it will just change the control loop will change the duty cycle, and it will keep on output regulated at 5.5 volt with variable input supply. For negative, so now we have 5.5 volt. If we invert that, and so for inverting we can simply use a charge pump, inverting charge pump, and we also discussed about this. I mean, how you generate V output equal to minus VDD or minus V in, and it's just a edge bridge, and you have a flying capacitor. So your output will be minus 5.5 volt, and this is nothing but negative charge pump. So it's a simple circuit, but it has a problem actually. So since we have we have switches here, and so they will have RDS on losses as well as switching losses. Okay. So based on the losses, when you apply a V 5.5 volt, there will be IR drop across these switches. So your output will never be exactly 5.5 volt, but below that. So let us say V loss is the total loss in the voltage we are getting. So your output will be minus 5.5 volt plus V loss, and V loss, let us say 100 millivolt, then instead of 5.5 volt your output will be minus 5.4 volt. So your this output will not be regulated exactly at 5. So we need to fix this. So in order to fix that, what we do, so what we can do, let us say this is I am getting 100 millivolt less, minus 5.4 volt. So in order to get this minus 5.5 volt back, I can regulate this voltage at 5.6 volt, 100 millivolt higher, so that I can get minus 5.5 volt, and then extra 100 millivolt I can drop in the LDO, and this will give me 5.5 volt. Obviously 100 millivolt will be dropout voltage here in the LDO, so that will be a loss in the circuit. So your efficiency will be degraded little bit, but if you have a requirement of exactly same voltage on both sides, then I mean you have to live with that, so you can't do. So you have to sacrifice some efficiency in order to match these two voltages, positive and negative. So now the feedback will be coming from here, because now we are interested in this minus 5.5 volt. So this will be fed back. So your this voltage will be regulated at minus 5.5 volt, and this LDO will try to, so whatever extra voltage here, now we do not care in order to regulate this, because this regulator LDO will handle that extra voltage. So now this LDO will take an input from here, which is obviously more than 5.5 volt, and extra voltage will be dropped across this. So now this feedback to this LDO will be coming directly from AVDD. So this will be locally regulated from this LDO at 5.5 volt. Okay, so this LDO regulates at VDD by dropping V loss voltage. So everything will be taken care by your control loop. You don't need to know how much losses are there in this. So okay, so another possibility is we can use inductive buck boost to generate minus voltage. This is a bit expensive obviously, because it requires one inductor. So and the output voltage now will be minus D over 1 minus D, and your inductor is connected to ground. So if you apply a volt second balance, you will know that this is the expression you get from here. So it's nothing but inductive buck boost. If this is a positive, we already know it's a buck boost, D over 1 minus D. So the only difference is it gets a negative sign here. So both have their own control loop. So 5.5 volt will be regulated by boost, and minus 5.5 will be regulated by buck boost. So it's a bit expensive, but in terms of efficiency may be better, because it does not require any LDO. Another possibility could be single inductor multiple output. Okay. So now we know how to do a inductive boost and how to do a inductive inverting buck boost. So if we connect this inductor in a edge bridge manner, which means 4 switches, and depending upon so what we do, it's like a time multiplexing, just like we saw in the single inductor multiple output. It's nothing but same, and we know how to control that. So it requires a edge bridge, and we will have now 2 feedback control, one for controlling the duty cycle of your inductive buck boost, other for positive boost converter. And this is how it works, and we already saw in single inductor multiple output. So, you allot like half the time to boost and next half time to inductive buck boost. So, it is nothing but it is more like multiplexing in time. So, in the buck mode, so it supplies, and one thing is you have to make sure it is operating in DCM mode, and it will be in DCM because the current required by these supplies is order of tens of milliohm or max 50 milliohm, not 50 milliamp, not more than that. So, so there is no issue of cross regulation and all those when your inductor current goes to 0, because it will be fully discharged before you activate the next phase or next mode. So, that is how it works, and depending upon the duty cycle, the current will change, and it will just supply keep the output regulated at plus 5.5 and minus 5.5 is coming here. So, if you apply a logic, you can exactly get the same thing. So, in the boost mode, we want this terminal to be connected to battery, and we want this node to be switching. So, your PWM will be applied on these two switches, and this switch will be permanently off. So, all the current will be supplied to AVDD, and the next mode or next phase, when IBB mode is there or inverting buck boost mode is there, what we want, we know that inductor terminal is ground, the other terminal, and so this switch will be permanently open, and now your PWM will be received by these left hand side switches, and your output will be here, which is minus 5.5 volt. Okay, so backlight requires LEDs, and these LEDs have a certain forward voltage. It is not like a normal PN junction diode which has a 0.7 volt, but these are much higher. So, mostly order of more than 3 volt or so. So, if it is a white LED, it may be 3.3 to 3.5 volt, and with the forward voltage, your forward current also changes, and these LEDs require constant current, because we know this current is exponential, has an exponential behavior with respect to forward voltage. So, if we cannot regulate the voltage as such, if we are regulating the voltage, even a small change in the voltage may cause a drastic change in the current. So, it is always preferred to regulate the current, and voltage, whatever voltage is required to get that current, the control loop will take care of that. So, these LEDs, most of these LEDs which are used for backlight, they have a full scale current of 20 milliamp or so, and now if let us say we have a sink current, and we have n number of LEDs connected in series. So, the total backlight voltage which is required here on the top of this first LED. So, it will be n times forward voltage of each LED plus the V-sense. V-sense is nothing but the voltage across this current sink actually. So, LED brightness is proportional to ILED. So, now you can see here intensity. So, by controlling the current, you can control the brightness of your display. So, backlight is basically supplied by this boost converter. So, what we know that we need to boost this voltage. So, let us say this each LED has roughly more than 3 volts. So, 8 LEDs may require roughly 28 to 30 volt, and in order to get this 28 to 30 volt from battery voltage, which is 2.7 to 4.6 volt, we need to boost it. I mean it looks like you are boosting more than 5 times here, even for the higher maximum voltage. Okay. So, when you go to 2.7 volt, that will be even higher. So, most of the time in the process we use this, it is a high voltage process, and we mostly get high voltage NMOS but not PMOS. So, for the high side FET, we put a diode, so it becomes a non-synchronous, not synchronous. Okay, so, it is a non-synchronous boost, and this is a Schottky diode, which is most of the time off chip. So, the on chip will be only this MOSFET, which is Mn. So, and you can regulate this current by having external current sense, okay, current sense resistor. So, now if this, let us say this resistance is highly accurate, and because the sense resistor which is off chip, and you can easily get a very accurate across your temperature, and tolerance will also be not that bad. So, now we know that if R sense is fixed, and if we regulate this V sense, then the current which is flowing through this LED will be nothing but V sense over R sense, and that is how you regulate. Now, in the feedback you know, I mean you can see it is a simple voltage regulator. Huh? So, feedback is voltage, automatically this loop will try to regulate this voltage. So, and there will be a constant current in the LED. But this technique works only for single string. Now, let us say if you have a multiple string, so you do not know which one to fed back, okay, or which one to feedback here. So now if you have a multiple string, so instead of using a sense resistor, what we do, we use current source or current sink. I mean you can put this current on the top also, so then you require a current source. When you are putting in with the bottom, you need a current sink. So now and the main reason we do not want to put it here, because as I mentioned, we do not have a high voltage PMOS here, and if you are putting here, then you require a PMOS high side. So that is why we are putting at the bottom. So if you have only NMOS, then you do not have any choice but put the current sink. But if you have a high voltage PMOS, then you can even use a high side current instead of low side current. So now this current regulator is nothing but a linear current regulator. Now we have on chip R sink, let us say this is Vref. So the current flowing here in this MOSFET will be Vref by I sink, and this V head is nothing but this voltage. So I sink is nothing but Vref by R sink. So now all these have a local current regulators. So this will ensure, as long as we have a good matching between, we know Vref is common, the only different component is this R sink. So as long as this R sink is let us say remains constant across these strings, different strings, then your current will be same in all the 3 strings. So but now you may ask that why this V head feedback is required, we already have a feedback here. So the reason is, still this voltage required is very high voltage. So how do we know what voltage to regulate at? So one way, like you can brute force way, is that if you know the what V head is required here, and you can add all the number of LEDs you require here, and then you know what voltage is required from this formula, okay. But that may change actually. Let us say I have designed a regulator to boost to this particular voltage, and somebody changes the number of LEDs in a string, okay, and let us say he wants to use the same regulator. Then what would happen? Obviously it will regulate the current, okay. So let us say there were 8 LEDs and the voltage required here was, let us say 28 volt or so. Somebody wants to use 6 LEDs, okay, and you are still regulating this at 28 volt. The current will be already regulated by this regulator. So with the, we have a extra voltage which is nothing but 2 times of Vf, and Vf is let us say 3.5 volt. So what would happen? 7 volt, where is that 7 volt extra going? It will be all dropped in this current sink. So this voltage will move up accordingly, because your regulator will in order to keep the current constant, the voltage across these LEDs should be constant. So extra voltage will come here, so that the voltage across, or VBL minus V hat, remains constant depending upon number of LEDs you require. So for 6 LEDs, obviously the VBL minus V hat will be lower. So extra voltage will be dropped here. And now when you are dropping extra voltage here, what you are doing? Eventually you are increasing the dropout voltage, and we know higher dropout voltage will give me poor efficiency. So your efficiency will degrade. So that is why we take the feedback from here, and depending upon the minimum voltage which is required to keep this regulator or keep this current regulated. So it will only boost up to that voltage. So it automatically take care. So let's say if I know that this is 100 millivolt, let's say this voltage, or this Vref is let's say 100 millivolt, and the extra voltage which is required, or VDS voltage required by this MOSFET, let's say another 400 or 500 millivolt, let's say 400 millivolt. So I know V head is 500 millivolt which is required in the worst case. So I can keep this regulated at 500 millivolt. So it will always make sure that this voltage is boosted to a level where this V head will always be stopped at 500 millivolt. It will never allow to go above that, so that I can keep the dropout voltage minimum and achieve higher efficiency. So no matters how many LEDs you use, it will take care of that. But one thing you have to make sure that you have to have same number of LEDs. Okay, otherwise you will again run into same problem, because the voltage required here will be based on maximum number of LEDs. So and this voltage is common. So if you are using lesser number of LEDs here, again this will have a higher dropout voltage and efficiency will go down. So now we have this current sinks, and if we let's say they can be programmed. So that is how you dim your brightness or control your brightness. So that is what the controlling brightness is called. The technical term we use for that is dimming actually. So what happens, you have on your menu, if you open the settings, you will see this brightness control on the slider, and as you move on the right hand side, if the brightness will increase, and when you move that on the left hand side, the brightness will be reduced. So all this from your basically application layer, the command is sent to the mobile processor, and mobile processor sends this command to the dimming controller, which is part of your PMIC, the LED driver we call, and that does nothing but controls this current, and that is how your brightness of the screen is controlled. So you can see on the left hand side the minimum brightness, right hand side is the maximum brightness based on in which direction you move the slider. So this can be controlled, this current can be controlled in different ways. One is PWM or digital dimming, other is analog dimming. So we will look into one by one. Adaptive brightness actually what it has a ambient light sensor. Yeah. So ambient light sensor is there on your cell phone. So it looks at I mean let us say I am sitting here under the light. So the light is quite high. So in more light you need more brightness to see the display, otherwise it may not be visible. So it automatically increases the brightness. If you are in the dark room, sitting in the dark room, so even with the lower brightness you can see everything. So it will reduce the brightness. That is how your adaptive brightness works. So the ambient light sensor will send the command to your processor, and processor will in turn again do the same thing. It will control the brightness. Okay. So analog dimming is quite simple. We know we have this sink regulator. So all we need to do change the reference voltage. So my current is nothing but this Vref, if I call it Vref LED, let us say, divided by R sink. So that will be your current. So you have a fixed Vref, and you can have a digital to analog converter to basically generate a programmable voltage. So and it has to be digitally programmed because the command I am getting is binary from processor. So it has to be the input has to be in digital, but how you control the output whether digital or analog, that is a different thing. So when I am controlling Vref, so which means I am controlling analog voltage, so that is why we call it analog dimming. So if my let us say my full scale current is 20 milliamp and with 8 bit D2A conversion, so LED current can be changed with the step size of your 80 microamp roughly also. Okay. It will be 255 I think divided by 255, usually get a -1. No, step size LSB is divided by 250 n minus 1, 2 to the power n minus 1. So let us say we have 4 bit, sorry 3 bit. not 3 bit is one, 2 bit. Okay, so 2 bit, one is 0 0. How many codes you have? Total 4 codes. 0 0 is 0, huh? Okay, then 1, 2, 3. Yeah. So 3 levels. So your LSB is 20 milliamp divided by 255. If full scale LED current is 20 milliamp and we want 8 bit D2A conversion, so LED current can be changed with the step size, what we call LSB, least significant bit, is 20 milliamp divided by 2 to the power n minus 1. So 255 levels we get. So you have 80 micro, roughly 80 microamp, will be slightly less than that, but close to 80 microamp. So each bit, each LSB will change this. So that's the resolution actually you can achieve in your brightness control. So it will look pretty smooth. With 8 bit, like you will get almost more like a continuous change in the brightness or your intensity. Okay, so most of the time 7 to 8 bit is good enough. So analog dimming using PWM, there is another possibility. So what we can do now, let's say we have input is so let's say this is your processor, and processor is can send a command over I2C. So this will be sending a digital code, and digital code will be programming this voltage directly. Another possibility is instead of sending I2C, it may send a command over GPIO, general purpose IO, and it may be in the form of PWM, pulse width mode. So duty cycle of this PWM will contain the code. So let's say 0 duty cycle means 0 brightness, 100 duty cycle 100% or 1 is full brightness. So in between any basically duty cycle will give you the level of brightness. So 50% duty cycle will give you the 50% brightness. So it's just proportional to your duty cycle. So what we can do, so this GPIO will have a different level, and I know my full scale voltage is Vref here. So I can level shift this this duty cycle to Vref. Now if I pass it through a low pass filter, then the reference voltage which is generated from this will be nothing but D times Vref. Just like here, your Vref LED was depending upon the code here, now it will depend on duty cycle. Okay, so now this will automatically be varying when you vary the duty cycle of this PWM. So what happens, you get the PWM from this GPIO, and we shift the level of this PWM voltage to Vref, because my full scale voltage is Vref, and you pass it through a low pass filter. So if the cutoff is this low pass filter is much lower compared to the switching frequency of PWM, so you will get a pretty much a DC voltage, just like we get in switching regulator. Okay. So your output voltage of this low pass filter will be proportional to duty cycle, and Vref is constant. So by simply varying the duty cycle, we can vary this voltage, and my current is nothing but Vref LED by R-Sync. So that's how you change the current. So the current will still be continuous current, but this voltage will be varying with respect to duty cycle. So next one is digital or direct dimming. So in the digital dimming, what we do actually, instead of programming the voltage, we simply turn on and off the current strings. So let's say this full scale current is 20 milliamp again, and depending upon at what rate, I mean what frequency and duty cycle I am turning on and off. So it will look like a continuous to our eyes, because our eyes cannot perceive anything beyond it has to be done beyond 1 kilohertz. Even though our eyes cannot see anything beyond 100 hertz, but it may vary from person to person, and some people may perceive a flicker even 100 or 200 hertz. So that's why in order to be safe, we just keep it above 1 kilohertz. So when we switch this current on and off at 1 kilohertz, then at a certain duty cycle it is being done. So what would happen, it will averaged out by our eyes. So our eyes now acting as a filter here, just like we had a filter here to convert that duty cycle to a voltage. So now this duty cycle is multiplied by this full scale current, and then our eyes will see a continuous brightness. So, when the duty cycle is varied, it will look like a constant or continuous variation in the current to our eyes. So, the only thing is that your voltage will be changing, maybe changing a lot actually, especially this voltage. So, when it is turned on, it will be your, we know that a V head voltage or dropout across that. When you turn off, then this may quite possible it may go high. So, it will be creating more like a switching voltage rather than a continuous voltage. So, there are some EMI concerns with that, but it is usually taken care by the design and layout. Okay. So, just like I said here, EMI concerns. So, if let us say we are turning on and off these 3 currents simultaneously, so the current seen by the ground will be 3 times of each current. So, let us say 20 milliamp in each, they are are having full brightness. So, 60 milliamp current you are injecting in the LEDs and this ground and taking out, and these LEDs most of the time are connected through a flex cable. They are on a separate board, they are part of your display, and this current driver may be sitting on your PMIC, which may not be part of your display, most of the time it is outside that. So, they are connected through flex cable. So, now you can imagine that you are drawing I mean switching 60 milliamp current on and off, and these cables have high inductance compared to short traces which are on your PCB. So, it may be, there may be some EMI concerns. So, what we do actually, we turn on and them off in staggered manner. So, instead of simultaneously, what we do, we shift them in phases. So, we stagger them, and now at one time you will see only one LED is turning on, next time this LED is turning on, and then this is turning on. So, now you will not be basically injecting the same amount of current when these are turning on and off. It will be reduced actually, because at a time only one LED is on. So, you will be injecting only the 20 milliamp instead of 60 milliamp. So, obviously, if duty cycle is much higher, then at that time you can see all may turn on simultaneously, but as long as your duty cycle is lower, you will see it will not be a problem in that case. Okay. So, now let us move to this power management for AMOLED displays. So, AMOLED displays, as we know, it does not require backlight as we know, as we need in LCD, and the reason is that it is LED. So, it has its own light. So, the supply requirement is different for this, and what we require, again 3 supplies here just like in LCD, but these voltage levels are different here. So, we require negative buck boost or negative supply, just like we need in LCD. We require positive boost also, and ABDD is different. So, now in the negative voltage required in LCD was fixed minus 5.5 volt, and positive was fixed 5.5 volt. Here negative voltage is varying, it may be from minus 0.8 to minus 5.4 volt, and if you look at the current requirement is much higher, 300 milliamp. There we required maximum 50 milliamp or so. So, that is the main difference. Then positive voltage is fixed 4.6 volt, but the current requirement remains same, because you can think about they are this supplies is connected across these LEDs. So, whatever you are sourcing, you will be syncing the same. So, that is why the current requirement is same for both positive and negative. ABDD is again required for some analog and in the driver. So, it requires 7.7 volt. In case of LCD, we required more than 20 volt or so, because it was required for backlight, which was supplying those series LEDs. So, again this is the control signal comes from this display. So, to turn on and off, and This S wire I will talk about, it's a serial single wire interface which is used to control this voltage actually, vary this voltage. So these are the supplies. So supply requirement is number of supply we require is less compared to LCD here. So 1.8 volt for your digital and analog 3.3 volt, then 4.6 positive minus. So this could be, I am mentioning here minus 1.4 and here minus 0.8 because older displays required only 1.4 minus 1.4 lower, but now our newer displays are requiring minus 0.8 volt. So the minimum voltage. So and then 7.7 volts. So these three supplies, just like in LCD, mostly have are external, and these two 1.8 and 3.3 part of your DDIC. So this is your basically could be part of your PMIC, or it may be a dedicated power IC for this. So why do we require a fixed 4.6 voltage? This 4.6 volt, and this is varying. So let's look into this. So we know this is LED. LED requires constant current. So what happens? Your so let's say this is your current source, and you are mirroring this current to your LED. So now you turn on this switch, and this voltage will be sampled by this capacitor, and it will be held here. So and we know this switch is basically running at a very high frequency because it depends on your refresh rate obviously. So it will be scanning or sampling and then holding this voltage, and this switch will turn off. So when this switch is turned off, so and let us say any change in this voltage happens, that will be directly reflected into this LED, and this current will change because this voltage is already fixed. But if this switch is turned on, then if this is changing and I have a constant current, so this voltage will automatically change, the gate voltage. But that same thing will not happen when you do not have this switch on. So during off time, if any change happens, it may get reflected and change this current here, and that may, so if let us say that noise is a very low frequency which may fall into your visible frequency range, let us say 100 hertz also. So this may appear as a flicker to you. That is why we require a very clean supply 4.6 volt here. Okay. So that's the main reason actually we need vary. So any ripple here again, any change here will change the current, and that is why we do not allow any variation in the supply, and we need a very clean. And this could be happen at your GSM bus. So during call your bus frequency is 217 hertz, or it may happen at 120 hertz coming from your wall adapter. So this frequency may be coupled to this supply and may appear as a flicker to our eyes. GSM burst is basically when we make a call, your power amplifier actually you transmit the signal. So that is transmission is done at some particular rate, which is 217 hertz, and that is what we call GSM burst. But this rate is much lower when you are not making any call. When phone is standby mode, it will be pinging actually just to check that whether anybody is making call or not. So but the moment the call is placed, then this frequency will increase.